afternoon, everyone. Well, thank you for joining this workshop. We will talk about creating dedicated digital twin by experience. So in this presentation, we target everyone curious about machine learning techniques and also data scientists. There will be a bit of code, but of course, we will provide you some explanation during all the presentation. And please don't hesitate to raise the hand if you have any question. We'll try to do some checkpoints to check if everyone understands well and is still here. So I propose to start with a quick reminder about what is a digital twin, and after we'll go a bit further into this topic. So a digital twin, basically, is a virtual model designed to reflect physical object or process. Its data come from sensors and is applied to this digital copy. So digital copy will react to this data, provide some outputs, and the outputs are shared back with the original object. For example, if we stay in the scope of the InterQ project, let's take, for example, a blockchain machine. For inputs, you would have, for example, the power, the torque, the position, the accelerometers, and for output, the quality measure. Basically, what the digital twin will do is try to predict the quality measures. But where we differ from the simulation is this quality measure will be sent back to the physical object or process so that it can act accordingly to the result. So, for example, if we observe a lack of a decrease in the quality, basically we can raise an alarm or stop the process. On this slide, I put a link to the IBM website because I think they have a nice explanation about what is a digital twin, and especially they give us a bit of terminology, some use cases, and I found this page very interesting. So I put it in the slide if you want to check it after this meeting, and if you want to have more information. So for today's agenda, basically, we'll try to follow this plan. So first, we'll present what we do, so what DataThings are building. Then we'll focus on the use case. And then we will basically try to follow all the steps we are used to deal with machine learning and digital twin. So how we gather knowledge, how we use the data, and then how we exploit the results. And for a conclusion, we'll give you a bit of introduction on what is DataThings and how we can help you to build such digital twin if you have such needs in your, I would say, everyday business. So at DataThings, we are providing a solution called GreyCat. So GreyCat is our core technology. It is a state-of-the-art product dedicated to temporal graph and data analytics operation. In GreyCat, we have an in-house machine learning stack, and basically we use this stack for every artificial intelligence training. To ease a bit the operation, GreyCat provide its own programming language so that data scientists and domain experts, with of course a bit of programming skills, can build and run their experiment. The technology is domain agnostic, so it can be applied on industrial use case, but we're also using it for energy use case, for the finance, for advertising. Almost every domain that deals with data basically can be addressed with GreyCat. We focus the technology to be able to run on huge data set on community hardware. Of course, there is always a limitation in speed with an everyday computer, so GreyCat scales on a distributed infrastructure. And during this workshop, basically, we will illustrate how GreyCat can be used to address some of our use cases, and mostly use cases related to the manufacturing of jet engine parts. So I will let my colleague Alexandre to present a bit the use cases.
So the use case that we want to reflect around today is obviously comes from the InterQ the InterQ use cases that we are working on within work packages 2 and 3 today, which concern both manufacturing processes of jet engine parts. So as an illustrative example, we focus here on the Trent 1000 jet engine, for which we saw a part during the general meeting in Bilbao. So it's just an illustrative that can reflect a little bit what everyone has seen.
Sorry, Cyril, is the microphone muted?
Yes, you're muted.
Alexandre, you're muted.
Hello?
I think it's Alexandre who's
Hello,
muted.
hello?
Are you
Yeah.
hearing us
Now
again?
it's fine.
Perfect.
Yeah.
Yes.
Now we hear you.
Yeah, sorry. I don't know what you missed exactly, but just to give you a little bit of context here, one of the use cases that we are presenting today will be on the milling of internal casing of jet engines. So this is the part that we show here in blue, which is a long process, around 40 hours, with many various operations did on the part itself. And on the other hand, we have the use case of the WP3 work package 3, which will concern the broaching on fin holding slots on disk. And these are rotative disks that are placed highlighted in this part of the engine. And basically, this is really much faster processes and very repetitive, with each broaching during around a minute or so per slot. With a lot of slots, the whole process takes a bunch of time, a few hours, but the broaching per slot is really, really quick. And yeah, so this is the part where we also in Bilbao, and just to give you a little insight, every slot that you see on the rim of the disk is exactly what is broached during the process that we are focusing on. Any question here, maybe? Don't think so, but
No,
sorry.
no raised hand.
Yeah, we can go on.
Yeah. So now that the use case has been presented, basically we will go through the different steps of building a digital twin. A preliminary and mandatory step is first to gather ground knowledge. So to do that, we spend time with our partners to understand their business and their problem. Basically, this is the step where we identify the data needed to solve the problem. Then we will focus on collecting the data. Where the data is located, is it accessible data? Do we need to access third-party system, or do we need to deploy new sensors? And then we'll need to prepare the data. So we have some partners say the data is clean, but from our experience, data is never 100% clean. And we will focus in this step on the gaps in the data, the outliers. Well, we'll try to prepare the data as much as possible for the training processes. So in gathering ground knowledge, the ultimate goal is to understand the partner's domain of expertise and to define a behavior in this process. To collect the data, we often need to access a remote endpoint or API. Well, it is more efficient to have remote endpoints than sending an hard drive by email. And for that, we have integrated directly into our GreyCat technology connectors and parsers.
Yep. So as an example, we have here a little bit of a code that is written actually in GreyCat, our internal solution, which is able to get some information from an Aeromech API, which is one of the partners that we are working with within Work Package 2. And as we see here, we have a bunch of stuff that can be expressed, but the more important part here is that we are showing here is that we have So some libraries that are basically dedicated to data collection, such as the HTTP and JSON APIs that we see here, but we have also the possibility to easily parse CSV files and all these sort of things. And basically, the data that will be available after such parsing will represent as this within the WP2 use case. And one of the important parts here that we want to show is that basically what we get here is a lot of stuff that is obfuscated by internal API identifiers that are not easily to make up much of sense for human, because basically, okay, we have here 4 features that are just given a weird identifier, but the API is also able to provide a lookup table in order to have some more human understandable identifiers. And by using this lookup table, we are able, in the end, to make sense of what we are collecting here. And yeah, I think that's it on this slide. So yeah, the idea towards the gathering of ground knowledge is to get a data set. The main objective is to get a data set that can be used towards what we want to do with our partner. And basically, yeah, the more data, the better, both in quality and quantity. What we want to have is meaningful and plenty of data that which are both mandatory and hard to get most of the time with industrial partners. So when we are talking about quality, what we want is that the data set must reflect all possible events that we are interested in the production process. And concerning quantity, basically data analytics works better with a lot of occurrences and provide better results with this. And yeah, from there, as a second step, it must be also possible to consolidate data collected from different sources. The consolidation raises both matching and alignment issues. So basically, okay, we have maybe 2 files that concern the same process, the same actual process that took place yesterday, but how do we know exactly how to match those 2 files? And you might have also some alignment, temporal alignment, more often than not, issues that will arise with basically, okay, we have some timestamps maybe in one file, but not in the other, or the timestamps in both files are not perfectly aligned, and there is some work to do on this, and this is a lot of questions that we have to tackle when collecting the data and cleaning the data, basically, to prepare it. And what we want to have towards any analytics is 2 kinds of metrics that can be extracted from the data, which we are naming from the machine learning vocabulary, which will be features or metrics that closely predate or happen with the behavior to be studied on one hand, and on the other hand, labels are the metrics that, depending on their values, are known to define the occurrence of the absence or the absence of the behavior being studied. And yeah, the features and label must also concern the same actual process to be of any use. Because if we have features that concern one process and labels that concern another, it's useless to us because we can't make any use of them.
So now that we have the data, we need to perform several steps. The first one is basically data cleaning. For example, if we stick to the AeroMake use case, for the same machine, we have data located into various places with different sampling rates and timestamping. For example, you would have data with a 1 second sampling rate and other data at 1000. It was 1000 hertz of sampling rate. So if we want to correlate this data, basically we have to align everything. The goal of that is that at a single time point, basically, we can retrieve all the data. And to do that, in GreyCat, we can define time series. So for example, 1 per feature. And we have a resolver that tackles for you the data alignment problems. We also need some time to predict new features, to engineer new features. For example, with AeroMake, we try to predict the stop in the near future. But to predict stop, basically, you need to mark the stop into the time series. But unfortunately, we don't have a stop time series for the partners. So we have to infer this time series from the other feature we have at our disposal. For example, at Aeromech, we have two features, one called op mode, one CNC op mode. So you can see that there is a misalignment between the data points. So they are not exactly one in front of each other, but we are able to infer a new feature, the stop feature, that basically is a timeline saying that in green the machine was working, or in red the machine was stopped. And now we will show you a bit of code. So basically, based on these two features, so the op mode and the CNC op mode, how to build this time series.
Yep. So, yeah, as for the code itself, what we want to define here is basically a collection of time series that will be able to store the data from both the op mode features and the stop label that we want to generate. And the idea here is to have a really simple model where we just have an associated table of time features identified by their feature. So we have an enumeration feature that will be shown quite quickly afterwards. But first, what we want to do is actually generate a new label from the data, which will be the stop that we want to mark. And for such a task, we define simply a function that will be in charge of marking the stops. And the first thing that we want to check if we have actual data in the model, because if we don't have any, well, you have to load the data first, quite obviously. And yeah, basically, once we know that we have data, we get the actual time series from both op mode and CNC op mode. So as I said, they are stored by an enumeration feature in which we have the op mode, the CNC op mode, and a little foreshadowing with the stop, which will be our label. And yeah, from the stop, what we want to do is clearly create one new time series, and that will be added to the model. And then we set it up like this. And once we do that, we want to go through the whole data set and check whenever some conditions are met. The conditions here are simplified, and the idea is to say, okay, whenever op mode and CNC op mode are 1, all is okay, but if they are both zeros, then it is a stop. And it is what is shown actually on the 3 time series on the right here. And the idea is to say, okay, we are going through the whole data set, but the way we want to do that is by going through one of the time series and aligning data from the other time series, from CNC op mode, in order to know what is happening at every time point that we are encountering in this way. And yeah, one of the first steps that we want to do is mostly focusing on working hours of working days. And for that, we define a method validate timestamp that if it's not matching, then we just keep the loop, the step in the loop.
Yeah, the idea here of validating the timestamp basically is we don't want to have data points rated basically on weekends or during the night, because from what we have discussed with the partner, we know that there is no production at this time.
Yeah. And so the way we actually do the stop of markings, once we have pronounced the off hours, is that we also get the CNC up mode value. So for that, we have a call that we can do on the time series, which is resolve that, and it will be able to get the last value known at the given timestamp, which is quite interesting because as the data is misaligned, as we see here, we will be able, for instance, to get the once we get to this up mode value where we are at 0, just right here, we can get the CNC up mode value, even if it's not aligned, it will get the last one, which is 0, that can be seen here. And from there, we also have the possibility to know what is the time where it is resolved with the call to resolve timeout that we can see here. And thanks to that, we are able to express some additional condition checking on the alignment. And if we want to say, okay, maybe we won't consider that the 2 time points from both time series are not aligned. If they go over a certain threshold, we have the possibility to express it, and this is what we are doing right now. So in addition to actually validate also the CNC timestamp, we want to check if the difference between timestamp and CNC timestamp won't go over a certain threshold. And the interesting part here is that we can actually define whatever the threshold we need, and we are really agnostic and can adapt to any need of the client. So here, for the instance, we define just right here the threshold at a duration of 5 seconds. And but it can be anything. And at last, we have the possibility simply to express the condition that we want, is that data stop will be marked whenever we have the up mode that is different to 1 and the CNC up mode that is different to 1. And then we just have to set it in the timestamp with a really easy call to on the time series in itself.
Yeah, so just to summarize a bit this code. So you can see that with GreyCat, basically, we can handle time series. We can resolve the time series at any time point you want. And basically, GreyCat will handle for you the data alignment. And we can, in an easy way, express some conditions. So here for the stop, it's just checking that the up mode and the CNC up mode are different than 1. And with this condition, we can create a new time series that we will use later for our learning. And this new time series basically is a new feature. So now we'll use the data.
Yep. So as towards using the data, well, depending on the data inherent quality and limitations, we have 2 main approaches to deal with it, which is if we have enough data for both normal and problematic behaviors that we want to study within the monitored system, the machine learning approach ends at yielding AI techniques to infer from the data a digital twin that will be able to predict the problems that we want to actually predict. And if we are in a case where most of the data and there is a dramatical imbalance between the normal data, which will be overrepresented, and problems that are really rare, and this is more often than not the case in industrial use cases. Then we have the possibility also to provide some sort of a profiling, which is also a complementary approach to the machine learning. For which the idea is basically to provide some sort of a fingerprint for a normal process, such that whenever the fingerprint goes out of the profile, we will simply when a process goes out from the profile, we will consider it problematic.
So we will show this different step now.
Yep.
So we'll start with the machine learning. So from the analysis we perform on the Aeromake data set, basically we observe that we add a subset of features that deviate the most from their normal behavior before a mark stop. So to do that, we display the time series, we perform the analytics, we add our stops marked with the new feature we had just generated before, and we saw that almost 30 seconds ahead of stop, there was some interesting stuff. We had some interesting variation into the data that leads us to think that this stop could be predicted at least 30 seconds ahead.
Yep. And so the idea of the approach that we are going to show here is to make use of this with an LSTM neural network. So basically, the approach of LSTM, which stands for long short-term memory, is to predict a future data point from a time window of fixed size of the last data point. So this is shown in this time series, just right here, where we are focusing only on one feature for the example, but basically we have here some sort of history, which we are calling the LSTM history. And from now, we want to predict some data in the near future. So the near future is basically 30 seconds ahead as we are talking right now. And the way that we can express this will be shown in the code right now. So as for the code, what we want to have is to declare some sort of a predictor that will be in charge of training on the model, on the data, of training a model on the data in order to make predictions down the line. And yeah, what we are showing here is something that might be a little bit familiar to Python machine learning data scientists. With some sort of with two tensors, which are the input tensors and the output tensors, and the possibility to express their shapes as arrays. So just to give you a little bit of context, tensor in machine learning is basically an n-dimensional array, which is able to represent stuff with a lot of indices. And basically what we want to have within LSTM will be an input tensor of 3 dimensions and an output tensor of 2 dimensions, but we will get in more details just right now. So the first step towards the training will be to prepare the data, because basically we have a data set which is basically in the form of a time series of data points. Any data point is an array with a value for each different feature that we want to train on. And but basically every data point is only one dimensional and concern only one time point. And as we just saw, we have to also provide a way of dealing with an history for LSTM to work. So we have to prepare the data towards this, and we also want to get the data that we want to predict, which is 30 seconds in the future. So basically here we can see that we are passing some information as parameters. So the prediction span will be our 30 seconds, and the history span will be the size of our LSTM history. Concerning the, sorry, it's just a little bit. So yeah, but basically what we want to specify right now is the size of both, the lengths of both our tensors, the input and the output. That will be a little bit less than the whole data set because of the history size and the prediction span size. And also we are dealing with the width of the data set, which is basically the width of any time point. We are supposing here that the data is well prepared, is well formed, with basically any time point having exactly the same width every time. And the way it is done is really something familiar for Python developers, with the possibility to express the shape as it is shown here, and to initiate the tensors with the shape. And from there we get, okay, so the first, the boundaries that we want to go through all the data set. So basically we'll print out the first history span values and the last prediction span values, just to be able to actually build some history even for the first data point that we are working on, and some future value even for the last that we are dealing with. And from there, the way that we can go through our time series is of this form. We have the possibility to express a for loop that will go through all our data from to. And yeah, this is maybe one of the hardest part for non-Pythonian and non-data scientist. But basically, the idea is here to put in the input tensors the values, all the values for building a history. So we are going back to the 17th step of our history, for instance, and putting every of these 17 values. And we then do the same for the output values, which will be the one predicted a little bit ahead. So this might be a little bit hard, but the important point here is that that we want to focus on is that basically we have the possibility to express with the same ease what can be expressed to what the standards provide. So once we have prepared the data with this big method, what we want to do afterwards is basically prepare the model, then train or feed the model. And yeah, what we are declaring right now in predictor in the predictor will be a sequential network, which will host the LSTM layers that we want to that will do the job of training on the data, and a compute engine that will be able to execute the neural network and the training, the training of the neural network. So what we want to do is actually to prepare the model, then train, and we declare two methods to do that. And for the first method, we declare the sequential neural network as such. So we give it a really straightforward parameters with the input shape, the output shape, and the type of the data, which will be floats. And the idea afterwards is to add several LSTM layers in a way that is really, once again, standard-like and will reflect what people can know with Python, with the possibility to give, okay, this will be the number of neurons as the first parameter. So this will be the data width, etc. We do that for actually here for 2 layers. And we have then a dense layer that is able to restrict the data to the prediction that we want to predict. And okay, the optimizer, the loss is really common also. And then we have the possibility to express a lot of things in order to define in the end the batch size and the batches that will be used during fitting the model. And for the fitting of the model itself, this is something really more straightforward, with the possibility to express the round that we want to train on. And for each round, what we do will be to initiate a loss, and then actually running the learning algorithm, the learning engine, other on our neural network in order to on every batch, in order to update the loss, and we can afterwards store the loss in an array in order to plot it and analyze this down the line.
Well, just to summarize a bit for non-machine learning people, so this big code basically shows that we can use the ML stack from GreyCat basically to express machine learning algorithm. So for machine learning, you have several layers, so we can express in an easy way these layers, and we can as well add some parameters and optimization directly to this model with GreyCat code. And then to fit the model, basically it's the same. So we just need to provide the data to the model, and GreyCat will do the training for you. And if the model after converge, basically you will be able to have your predictions.
Yeah, and so in practice, what we wanted to do within WP2, because we use this approach within Work Package 2, was to empirically model the correlations between the labels and features related to the behavior to study. So the behavior to study was to identify the concernable behaviors of the machine that would lead to the stops happening. And yeah, from the data preparation, we were able to actually identify the features that deviate the most from the normal behavior. And as we said a little bit earlier, we saw that such deviation happened the most remarkably 30 seconds ahead of a stop. And the idea here is to use this to predict the risk of a stop within the next 30 seconds. And for that, we just say, okay, we know the recent history of the data, of the features. They are still okay, but we know that in 30 seconds, they will have a behavior that is really, really, really bound to a stop. And we have a high confidence that there might be a stop within 30 seconds because of that. And yeah, just basically we show here some results of the learning that lead quite good results. So with the loss that is plotted here and those actually converge, and more importantly and more interestingly, we are showing here that we have the possibility to actually stick really well to the behavior to predict.
So for the chart here, basically for ROMEC, these are the prediction up to 300 seconds, so 5 minutes. And we can see that if we change the prediction until 5 minutes, we are still able to predict something, I would say, that makes sense.
Exactly.
So that was for the machine. That was for the machine learning approach. We also have another approach that we can use with the data, and this approach is building a fingerprint model. Basically, we try to privilege this approach when we have few labels or no label at all. So it's quite a useful approach if you want to start right now to do something with your machine. If we have at our disposal some repetitive process without stop or problem, basically we can learn these processes by heart, and then we can confront them with a live data feed. So if we have trained the model with OK data, with data without any problem, basically if something bad happens, the model will automatically diverge, and so we can send alert to the operators. So it's quite as I said, it's quite a useful approach because we just need to observe a machine to collect its data, and we can build directly this fingerprint. To do the fingerprint process, basically in GreyCat, we tend to use a Gaussian object. So a Gaussian object is it's a statistical object where basically we have some useful insight, such as, for example, the mean, the max, the average, the standard deviation of data. And the idea is to use this Gaussian to know at a single time, at a single time point, what is the expected value. And for the live data, we face the live data with the average and, for example, one STD. And if we are inbound, we say, okay, it's good. And if we are outside, we can raise an alert.
Yep. So as an example, what we want to provide here is a little bit more complex model than the previous one. That will be mostly focusing on what we did on work package 3 this time with ITP. So we defined here a class which will be representing a manufacturing order, which will be identified by an ID, and which will, more importantly, will concern a disk model and that will be broached and some. Yep, some. And so yeah, a disk model will be identified itself by a serial number, and it will also collect two time series, which will be some data over its master engine and slave engines. And basically, the data that we will be collecting around both of these engines will be on three values for each time point, which will be the energy consumption of the engine, the speed of the engine, instantaneous speed of the engine, and the position of the engine during batching. So in addition to that, we are putting all of our manufacturing order within a time series. And this is an important part because it shows that we are able in GreyCat to nest time series with no real limitations depending on the needs of the partner. Because basically we have here a time series of manufacturing order, and each manufacturing order has itself two nested time series in it, but it's not a problem for GreyCat to run. And in addition to that, as we want to profile the thing that we are profiling right now is the energy consumption of the master engine for each of the disks, and the idea is only to declare an associated table of that will associate a Gaussian profile to a disk model. And this is what we are declaring right now. And basically, to profile this model, we have a very simple function that will be checking the same sort of stuff as before, initiate what we want to fill in, and for each of the manufacturing order, get the data and put it within the Gaussian profile itself, initiate the Gaussian profile if it's not existing, and finally add the data. And the idea is afterwards to compare the abnormal processes with the normal fingerprints. So, okay, we have defined a whole set of data that basically will only concern normal processes, and from there we have profiled them. And yeah, the way that we can compare these abnormal processes is by technically getting some useful information from the Gaussian profile, as stated earlier, and this insightful information as really easily get by dedicated methods on the profile itself, which are shown here. So concerning the exploitation of the results, we are focusing right now on one part which will be the how to use the models and how to deploy them in production. And yep, the objective of the using of the models is to make up useful information from the trained model. And for work package 2, we studied the performance of feeding back predictions into the model and showed that it still performs well up to 5 minutes chain predictions. So just to give you a little idea on this, we show here three traces, which will be, for once, the ground truth in blue, the rescale prediction that, well, the prediction that we are doing in red, basically. So this is a prediction 30 seconds ahead all around the time that we are making. And in addition to that, we are showing here a chain prediction 5 minutes ahead that still performs quite well. Obviously, it is a little bit more noisy, but it's not that bad, and qualitatively, when you are scoring some statistical analytics on it, you see that it performs quite well still. And as for deploying in production, the idea is to put back in the industrial loop useful information from the models. And yeah, more often than not, the goal ends up providing an indicator that helps to take decisions around the production. And what we are doing right now for WP2 is we define the risk score as the probability for stop to happen within the next 30 seconds to 5 minutes. And this is done with this workflow of decision. I won't go into details around it.
We can maybe just say that basically what we are doing is we are using the model into the green steps, and depending on the result of the model, so depending on the result of the digital twin, we can work on a risk score, and depending on the threshold on the risk score, send back an alert to the operator. Well, so this is the loop of the digital twin, because as I said in introduction, the result of the digital twin should be sent back to the physical object. So this is a demonstration of that. Here from the result, basically, we try to infer something to do on the original object.
Yeah. And basically, the core the core of the risk score computation is done with these predictions right here that basically use the trained model. And yeah, this is where we are actually using machine learning models in production in order to compute this risk score. And the deployment in itself consists of a black box that is able to push the computed score back into the Aeromech API itself in order to provide a new indicator. And in addition to that, we have the possibility to develop REST APIs or dashboards in order to access the model's ongoing predictions and make sure everything is going okay within the black box, and to give a little bit more of information than just the risk score computed back into the API. And yep, so we are finishing up the presentation of what we do right now with GreyCat within the InterQ project. So we talked a little bit around the gathering of knowledge, the necessity to understand the specific use case of our partner, the difficulties around collecting and preparing data towards analysis. We showed a little bit how we are using the data to try and build some useful information around it with both machine learning and profiling approaches. And finally, we just wrapped up the exploitation of results with building an exploitable information from the models and make this information accessible within the system themselves.
So these steps are not dedicated to InterQ. We are doing this step for almost all our projects. So it's quite a generic approach. I will just conclude this presentation by saying a few words about us, because we talk about GreyCat, but at DataThings, so we are a company that work every day with such kind of problem. So to give you a bit of history, basically the journey starts in 2013, basically when the founder worked on a solution to help industry in taking operational decisions. So at this time, they have started working on the foundation of GreyCat. And the company has been created in 2017 as a spin-off of the University of Luxembourg, because first the Luxembourgish market was asking for such solution, and now we can see that it's even the same abroad. During all this year, we have worked on many digital twins for many customers and across different business areas. So here we are at InterQ, we are working mostly with the aeronautical sectors for the use case we have, but we also working with the energy sector, the blast furnace. And just to give you an example on how important are these sectors, basically last year, NCO and Paul Wurt, so two big Luxembourgish players have invested in us to accelerate the development of GreyCat. And this year we reach the rollout phase of GreyCat, and we can now use it on, I would say now in a commercial way, and we would like other users to use GreyCat and see how we can perform on their problems. So so we have GreyCat to build this digital twin. So this is our core technology stack, but we also have expertise in different domains. So we have experts with dealing with complex data, with data in motion. We also have some machine learning experts, some people that are really good into scalability problem. So just to summarize, if you have any problems that require dealing with complex data, well, we don't bite, just give us a call or a mail, and we'll be very happy to discuss with you and maybe work with you as well. And thank you very much. So it closed quite, I would say, a nice coding event, the workshop. But now, if you have any question, please feel free.